Welcome back to the deep dive. Today we're jumping into a paper that could, well, it could really reshape how we think about scaling large language models.
It's called end-to-end test time training for long context.
Exactly. And our mission today is to give you a professional, really comprehensive look at the mechanism, the critical implementation choices, and the profound implications this has for long context performance.
And the challenge it's targeting is, it's maybe the biggest thorn in the side of modern LLMs.
It really is.
We all rely on the standard transformer architecture, right?
Yeah.
Full attention. It gives us this incredible near lossless information recall, which you just have to have for performance.
But it's computationally crippling.
Absolutely. The context length, T, you double that, and the cost goes up by a factor of 4. It's that quadratic scaling. It just makes modeling something like 128,000 tokens.
Okay.
Well, it becomes economically prohibitive fast.
And that quadratic wall is exactly why the field has been so obsessed with these purely architectural solutions, designing clever new blocks like Mamba 2 or Gated DeltaNet.
And those alternatives, they are successful at solving the efficiency problem. They get you that constant cost per token, that O of 1 we all want.
Yeah.
But as the paper really lays out, that efficiency comes with a pretty severe trade-off. Their ability to actually use those long contexts diminishes. They just don't scale in performance the same way full attention does.
And this is where TTT-E2E comes in and proposes something really disruptive. It's a paradigm shift.
It is. Instead of seeing this as a purely architectural design problem, they frame it as a problem in continual learning.
The result being they manage to get the performance scaling of full attention. So their advantage over the baseline is maintained as the context grows. But, and this is the key, with constant inference latency.
The numbers are pretty compelling. At 128K context length on an H100, they report TTT-E2E is 2.7 times faster than full attention.
While keeping that performance edge.
Exactly. This isn't just a small tweak. It's a totally different way of thinking about memory. They're compressing context directly into the model's weights, but during inference.
That framing, that continual learning idea is really the engine here. So let's talk about test time training, TTT. What does it actually mean in this context?
So TTT is this idea that the model continues learning at the exact moment it's processing your data at test time. As it streams the context, it's continually updating its own weights.
Like human memory, almost. The paper makes that analogy.
It's a good one. You go to a long seminar, you don't remember every single word years later. But your core intuition, your internal weights, they've permanently changed. The model is doing something similar, compressing the important stuff and letting the details go.
But if you just start updating weights on the fly, how do you stop the model from, well, catastrophically forgetting or just learning garbage? This is where the end-to-end part is non-negotiable, right?
Absolutely. The E2E is all about optimizing the whole process across 2 different loops. First, you have the inner loop at test time. That's where the active learning is happening. A new token comes in. The model calculates the standard next token prediction loss, the actual goal, and updates its weights with gradient descent.
And that's a key distinction. Older methods use these weird reconstruction losses that weren't tied to the real objective.
Precisely. So the inner loop absorbs the context. Then you have the outer loop at training time. And this is the trickier part.
This is how you prime the model, the initialization, to be good at that test time learning.
This is where the meta-learning comes in. And it is computationally intense. The outer loop is like a coach. You're not just training an athlete to run fast, you're training them to be an exceptionally good learner when they see a new track.
So you're optimizing the initial weights, W0, based on how well they perform after they've already gone through that TTT inner loop.
Yes, and to do that, you need to use
the infamous gradients of gradients.
Exactly. To get the loss for W0, you have to differentiate through the entire TTT process. It's optimization squared, basically. It's why training is complex, but it's also what makes sure the model starts in a state that's ready to learn, which is what those older TTT-naive models were missing.
Let's circle back to complexity for a second. You said constant inference latency, which is the O of 1 decode goal. But prefill is still linear, O of T. Why is that?
That's a necessary trade-off for this mechanism. Prefill is, reading the whole context once before you generate anything. And because TTT needs to run its gradient updates across that whole input sequence to compress it into the weights.
That process itself has to scale linearly with the length of the sequence.
It has to. So you take a calculated hit, a linear cost during that one prefill phase so that you can get constant speed for all the decode steps that come after.
Okay, that makes sense. So the concept is solid. How did they actually build this? They didn't design a whole new architecture from scratch, like Mamba.
No, they used a really practical hybrid approach. Their baseline is just a standard transformer, but it's augmented with sliding window attention, or SWA.
So just restricting attention to a fixed window size, K.
Right. For their big 128K results, they used a window of 8K. So SWA is like the model's short-term high-fidelity memory, and then the TTT part handles everything that falls outside that 8K window.
And I imagine the simple online gradient descent from the toy examples didn't scale. It must have been unstable or slow.
Oh, completely. Which led to the next big optimization, mini-batch TTT.
Right.
Switching to mini-batches, in their case with a size B of 1K tokens, it just makes things way more stable and parallelizable. But it also introduced this really crucial technical constraint.
The SWO window size, K, has to be greater than or equal to the TTT mini-batch size, B.
That's the one.
Why is that K greater than or equal to B constraint so critical? What breaks if the batch is bigger than the short-term memory window?
Well, if your SWA window is smaller than your mini-batch, the model literally forgets the start of the batch before the TTT update even happens. The SWA layer just moves on.
So it loses the local context it needs for the update.
It forces the model to rely only on that tiny weight update for context within the batch. The whole thing basically degrades into a bigogram model inside those batch boundaries and performance tanks. That constraint ensures SWA holds onto the context long enough for TT2 to absorb it.
This sounds like one of those cases where the implementation details are just as important as the high-level theory.
They absolutely are. There are 3 that are really essential to get the results they reported.
Okay, what's the first one?
The first one deals with stability during that very expensive meta-learning. They found if you try to update everything, embeddings, attention, normalization, the outer loop just becomes incredibly unstable. So they TTT only the MLP layers.
And freeze everything else.
Exactly. The MLPs are already designed for information transformation, so they turned out to be the most stable place to store that compressed context.
Okay. And the second detail was about finding a computational sweet spot.
Yeah, this is a really interesting finding from their ablations. You'd think updating more layers gives you more storage capacity for context, right? But the cost of backpropagating gradients goes up too.
And it wasn't worth it.
Not at all. They found that TTT only 14 of the blocks, specifically the last quarter, was optimal. Updating 12 layers, which is half the blocks, performed almost the same as just updating 6, which is a quarter. Huge computation win for basically no performance loss in scaling.
And the third detail gets at the classic enemy of continual learning.
Catastrophic forgetting.
Right.
To solve that, they introduced a static second MLP layer inside those blocks that get updated. So in those last 6 blocks, there's a second MLP that is never touched by TTT.
A kind of safe storage.
A permanent baseline, yeah. It makes sure that all these rapid test time updates don't just completely overwrite the model's fundamental pre-trained knowledge. It's knowledge preservation.
All right, let's turn to the results. Figure 1 is really the headline here. It shows performance scaling with context link, if you look at the loss delta.
Which is the performance advantage over the standard SWA baseline.
The TTT E2E line is just remarkably stable.
It's the definitive finding. As context grows from 8K all the way to 128K, TTT E2E holds a constant or even slightly improving performance advantage.
And if you look at the competitors, Mamba 2, Gated DeltaNet.
Their advantage just gets worse and worse. Their loss delta increases as context gets longer. This really confirms that TTE2E is achieving performance scaling that's on par with full attention.
And the latency results show the trade-off paid off.
Without a doubt. The latency is constant. Doesn't matter if the context is 8K or 128K. It really is the performance of a scaling full attention model, but with the speed of an efficient RNN.
So how does this whole approach integrate with general scaling laws? Does it still hold up when you throw massive training compute at it?
It does. They check that. When you scale models past 760 million parameters, or train on over 48 billion tokens, TTT-E2E's scaling trends just mirror full attention. The loss delta stays flat.
So the mechanism is robust. It's compute optimal friendly.
Yes. And interestingly, Gated DeltaNet showed a similar scaling curve, which kind of supports this idea that TTT-E2E is effectively acting like a very powerful hybrid RNN structure.
To really get the mechanics, we should look at the connection to their prior work, TTT-KVB, key value binding TTT.
Right, that was an earlier attempt. The core idea there was to compress context by binding key value pairs using a layer-wise reconstruction loss.
An internal objective.
And the key innovation here was just replacing that internal loss with the true end-to-end next token prediction loss. That one change got rid of the extra key and value parameters and massively improved performance. It just proved that optimizing for the real downstream task is what matters.
And what about where the model gains its advantage? The loss breakdown by token index is fascinating. They say the advantage over full attention comes mostly from the early tokens. Why would that be?
It all goes back to the outer loop, to that focused initialization. The intuitive reason is that the initial weights, W0, in the TTT-E2E model are only optimized to be good on the immediate mini-batch.
Because it knows it's going to update itself later.
Precisely. It doesn't need to be universally good for every possible future in the entire 128K context. But full attention does. Its weights are static, so they have to be a compromise, which limits how hyper-optimized they can be for the immediate present.
This whole mechanism points pretty strongly to the main trade-off of this approach, doesn't it? Compression versus detailed recall.
Absolutely. And they test this explicitly with the needle in a haystack tasks.
Where you have to find a specific string buried in a huge document.
And on those benchmarks, full attention just blows TTT-E2E out of the water, especially in long contexts. And that makes perfect sense. It confirms the design focus. TTT-E2E's strength is compressing and distilling knowledge. That means it might throw away irrelevant details, like a specific needle string, to maintain the high-level context.
Whereas full attention is optimized to do the exact opposite.
Right. It's built for nearly lossless recall.
So finally, we have to talk about the big practical hurdle that's still there, training latency.
This is the price you pay for the meta-learning magic. TTT-E2E is actually 1.2 times faster than full attention at 128K context during training, which is good.
But it's 3.4 times slower at the shorter 8K context length.
And that's where most of your training compute is spent in the early stages. The cost is all from computing those gradients of gradients in the outer loop and from using gradient checkpointing through time. It adds a ton of overhead, and that's the primary thing limiting its adoption right now.
Although the authors do suggest some ways around that, like initializing TTT-E2E from an already pre-trained standard transformer to skip some of that expensive meta-training.
That's right. And they also mentioned developing custom kernels that are better at the specific hardware operations needed for gradients of gradients. That could help with the hardware utilization bottleneck.
So to recap, this deep dive has really shown that TTT-E2E moves long context modeling away from just an architectural puzzle and into a really potent continual learning framework. You get the best of both worlds. Performance scaling like full attention with constant, fast inference.
And that brings us to the final, I think, provocative thought from this paper. By freezing some layers and updating others, they've essentially created a memory hierarchy. The TTT updated MLPs are the long-term compressive memory.
And the static SWA layer is the short-term high-fidelity buffer.
Exactly. So future research might not just be about improving how the weights compress context. It might be about developing even stronger, more expressive kinds of short-term memory to perfectly complement those continually evolving long-term weights. That integration, that's probably where the next big breakthrough is going to come from.